habis. So this is chapter 6. Chapter 6 is the last chapter calculation lah. In fact, chapter 6 the last chapter yang ada tutorial. Di chapter 7, 8 dah chapter membaca. So chapter membaca tu it's not that tough already lah. So chapter 6 is the last chapter dengan calculation yang can be a little bit difficult. But basically it's just satu equation saja. Kita belajar nak apply guna satu equation untuk kita selesaikan masalah. So why we have this extra equation? Sebab all this while daripada chapter 1 sampai chapter 5 we learn isothermal reactor. Means reactor tu the reaction doesn't have any changes of temperature during the reaction. So kamu kena faham reaction ni certain reactions are isothermal, meaning semasa tindak balas tu berlaku there's no change of temperature. However, there are also reaction where if we call it as non-isothermal, means semasa reaction tu berlaku suhu pun boleh berubah. So why this happen is because maybe you have heard, right, kita ada endothermic reaction, exothermic reaction. So endothermic reaction means the reaction needs heat. Exothermic pula maksudnya reaction tu akan release heat. So either way pun dia akan ada perubahan suhu, either kenaikan suhu or penurunan suhu, but it's still change of temperature. So we call it as non-isothermal. So non-isothermal ni dia affect reactor design kita juga. So whenever you have katakan when you deal with real reactor, it's very important for you to really determine adakah sebarang perubahan suhu berlaku semasa tindak balas during the reaction, or sometimes there are certain case where you supply heat to the reactor. So let's say let's tell you some reactions are endothermic. So endothermic they need heat. Okay, they need energy. So in this case, you will supply heat to the reactor. So in this case pun, kita kena consider dalam reactor design kita. So why this is because reaction temperature or the change of temperature during the reaction will affect our reactor design, which is the volume, because dia akan mempengaruhi conversion juga. Okay, so when conversion is affected by temperature, therefore the volume of the reactor pun akan berubah. So kalau kamu ingat, dalam volume tu kita selalu cakap pasal conversion kan, pasal X. So kalau temperature mempengaruhi X, so automatically volume pun akan berubah lah. So you have to really consider this when we are calculating the volume of the reactor or when we are designing the reactor. So the concept, kamu nak design reactor, dia dah tak sama kalau kita isothermal dengan non-isothermal. Okay. So apa masalah dia? Kenapa it's difficult for us to calculate the volume? Right. Okay. So kita buat satu andaian. Okay. Let's say now we have a CSTR, and let's say CSTR kita ni rate law dia first order reaction. Okay. So at the same time, kamu tahu kan volume CSTR kalau kita nak kira equals to FA0 X per minus RA. Okay, so katakan kita assume rate law dia minus RA equals to KCA. Okay. Sebelum ni pengiraan pengiraan K ni kita tak ada masalah sebab once we know the feed temperature, sebab reaktor tu kalau suhu asal kita tahu sebab kita prepare reaktor tu. So kalau isothermal, feed temperature tu kita dah boleh guna untuk kira K. Okay. Tapi masalahnya bila non-isothermal, kita dah tak boleh guna feed temperature sebab reaction temperature dah tak sama dengan feed temperature. Meaning, I might feed at room temperature, maybe about 30 Celsius, tapi because of non-isothermal, the reaction temperature is no longer 30 Celsius. So kan kamu ingat saya kata nilai K ni mesti ikut suhu tindak balas. So all this while is not a problem sebab kalau isothermal feed dengan reaction suhu yang sama. But now it becomes a problem because when reaction temperature is no longer the same as the feed temperature, I have to know my K at the reaction temperature. So now kita ada satu pemboleh ubah yang jadi masalah kepada kita because we don't know reaction temperature T. Okay, so tak tahu T tak boleh kira K. At the same time, Kita tahu concentration kalau kita nak express dalam bentuk conversion, A sama dengan CA sama dengan CA0 in bracket 1 minus X. Okay, so example kita buat example. So kalau kami ingat dalam chapter 4, kita akan combine kita akan combine equation 1, equation 2, equation 3, equation 4. So bila kita combine, kalau kamu tengok, kita nak cari volume, so it become FA0X. Sebab K kita tak tahu, okay, so kita kena masukkan Arrhenius equation ni lah, kan kita tahu perkaitan antara K and temperature is through this Arrhenius equation. Okay, so when we combine this, okay, it become a problem because now kamu tahu bila kita nak solve mathematical equation, kalau satu equation kena satu saja unknown, okay, yang maknanya selebihnya all the other parameters we need to know the value. Okay, so kita nak cari volume, means the volume is our unknown variables, but the problem is we have two lagi unknown yang kita tak boleh solve, which is conversion and temperature. Okay, so as long as I don't know reaction temperature and I don't know conversion, saya tak boleh cari volume dia. So this become additional problem when we want to solve the design of the reactor, meaning nak cari volume sebab kita tak tahu X, kita tak tahu temperature. T lah. Okay. So kalau kamu belajar mathematics, dia selalu kata kalau kita ada terlalu banyak unknown, tak cukup equation. Okay, kamu kena tahu kan number of unknown mesti sama dengan number of equation. Kalau kita terlebih unknown, tak cukup equation, kita tak boleh solve. So what we need to do, we need to find another equation. Okay, so how do we do this? Okay, so we will then introduce satu equation. Okay, we get the equation from the energy balance. Kamu dah pernah ambil CPP. It's actually equation tu derived from the energy balance, di mana this new equation akan relate conversion dengan temperature. Okay, meaning kalau katakan kamu tahu kamu punya targeted conversion, you will use this new equation to find temperature. Or vice versa, katakan kamu tahu reaction temperature kamu boleh gunakan equation yang baru ni untuk cari conversion. Okay, so the same lah, means throughout chapter now sebenarnya we will learn this new equation, and basically either you have conversion, you find temperature, or if you have temperature, you will find conversion. So bila kita dah dapat dua pemboleh ubah ni, we can solve X and T, then baru kita boleh cari volume. Okay, so energy balance equation ni is based on our first law of thermodynamics. So saya tak akan explain lah how you derive. Kalau nak explain pasal derivation ni, actually it will take another 5 to 10 slides untuk derive how you get the final equation. But as you know, okay, yang penting for us is actually to solve problems using the equation that is derived. Okay, so I will go directly to the equation. Okay, dia punya pro dia, equation ni bagus sebab dia boleh cari perkaitan temperature and conversion. Kalau kamu perasan dalam equation dia ada T, ada X. So means ada either you tahu temperature, kita cari X, or kita tahu X, kita cari temperature. The cons dia ataupun kesusahan chapter 6 ni adalah kalau kamu perasan equation ni memang panjang. That's one thing. Okay. Kedua, in this equation kamu tengok ada banyak terms. And dalam setiap ataupun unknown, and dalam setiap unknown ni akan ada sub equation lagi, and this sub equation pun boleh berubah depends on the reaction. Okay, so that's the difficulty of chapter 6. Satu equation tetapi dalam equation ni ada sub equation lagi before we can use the entire equation. Tetapi yang penting kamu kena ingat, bila kamu tengok equation ni, dia punya kegunaan dia is either we have reaction temperature, we find conversion, or we have conversion, we find reaction temperature. Okay. So now my responsibility, my job is to explain to you one by one apa unknown dalam equation ni. Okay. So the first unknown, kita akan start from left, is Q. So Q ni kamu dah belajar CPP, kamu dah belajar thermo, kamu tahu Q is always used in chemical engineering to represent heat. Okay, so maksudnya if you are introducing heat to the reactor or you are supplying heat to the reactor, kita panggil sistem ni sebagai non-adiabatic. Okay, so mungkin kamu dah pernah dengar perkataan adiabatik. So non-adiabatic means they are Q. Okay, their heat is supplied to the reactor. We call it non-adiabatic. Okay, nanti kemudian kita akan belajar adiabatik. Apa beza dia? Kalau adiabatik means Q0, means tak ada, there's no heat supplied, and also there's no heat transferred from the reactor. Okay, so kalau non-adiabatik kita kira Q. Kalau adiabatik, Q tu kosong. Okay, so in the case of calculation of Q, Q ni pun kamu kena faham, kita nak kira how much heat added to the reactor. Okay, it's also not straightforward. Dia ada equation dan equation ni akan berbeza mengikut the types of reactor. Sebab tu, for this chapter 6, non-isothermal, I will only cover CSTR. Sebab kalau kita cover batch, kita cover PFR, is entirely bukan different lah. The calculations and the design will be more complex. So apa yang kita cover dalam chapter 6, which is CSTR, which is very commonly used lah, very commonly open system yang kita guna biasanya lah CSTR. So we will only cover non-isothermal CSTR. Okay, so kalau you're talking about CSTR, we want to calculate Q, means kita nak tahu berapa banyak haba, how much heat is supplied to the reactor. We have an equation that is already provided, and this equation says Q equals to UA in bracket TA minus T. Okay, apa maksud equation ni? Okay, nanti bila kamu buat lab next week pun kamu akan perasan our CSTR, we have dia macam ada dua vessel. Okay, the internal vessel with the stirrer is actually your reactor, and you can see luar tu ada satu lagi vessel yang menutup your CSTR. So this outside vessel is what we call as either heating jacket or cooling jacket. Okay, so depends lah. Kalau the function of the jacket is to heat up, kita call heating jacket lah. If the function of the jacket is to cool down, then we call it cooling jacket lah. Okay, so in this our CSTR case ni, let's say we want to heat up. Okay, means we want to heat up, so it's a heating jacket. So kalau ada heating jacket, of course kita akan ada juga fluid ataupun we call it as heating element. Kita kena ada satu elemen yang untuk memindahkan haba. Okay, so we call it heating fluid. So this heating fluid pun depends lah. Okay, depends on the temperature that you want to use. Sometimes you may use water, sometimes you may use steam, sometimes you may use oil, so on and so forth. So the element of the criteria to choose for your heating fluid depends on what temperature that you want to achieve, means what temperature that you want your reactor to achieve. Okay, so to calculate the Q, okay, this U refers to heat transfer coefficient of the jacket. Okay, A is the heat exchange area, so your jacket area. So let's say kalau kita assume, let's say we are talking about using steam, saturated steam to heat up your reactor. So the A is also equivalent to the steam jacket area. Okay, then in bracket TA. So TA ni adalah heat transfer fluid inlet temperature, the inlet temperature of your heat transfer fluid. So let's say dalam case ni kita buat assumption kita guna steam. Okay, so it must be at the steam saturation temperature. So TA is steam saturation temperature, and T is your reaction temperature. So naturally sebab memang heat transfer takkan perfect kan, takkan 100% efficient. Sebab tu kalau kamu perasan heat transfer fluid kamu, inlet temperature dia mesti lebih tinggi daripada reaction temperature, because we know dia takkan perfect, dia takkan 100% transfer the heat. So katakan kalau heat transfer fluid kamu 100 Celsius, kamu takkan dapat 100 Celsius dalam reaktor kamu. Definitely there will be less of not so efficient. It will not be 100% efficient. That's why the heat transfer fluid temperature akan minus reaction temperature. Okay, so means kamu kena faham equation yang panjang ni, means benda pertama kalau dia non-adiabatic, okay, kamu kena kira Q dahulu. Dah dapat nilai Q, masuk dalam equation yang besar ni. Okay, so that's one. Okay. Next one is WS. Okay, WS ni kalau kamu perasan is actually we have learned in other courses, it always refers to work done. Okay, and in this case is WS, work shaft. Okay, itu shaft work, they call it as a shaft work or work done by the reactor. Okay, so depends. If you're talking about CSTR, the work shaft is actually referring to the work done by the stirrer. Okay, so kamu kena ingat, stirrer tu pun juga pergerakan, the movement of the stirrer also is considered as work, which also must be considered in the energy balance. Okay, so WS refers to, kalau CSTR refers to the stirrer, kalau PFR refers to the turbine. Okay, tapi dalam kes kita fokus CSTR lah. Okay, WS ni kita tak ada equation. Okay, so kalau ada pun value WS ni, it will be given directly to you. However, most of the time, the value of this WS is actually considerably smaller compared to the other parameters in your equation. Maksudnya, kalau kita nak banding nilai WS ni dengan nilai Q, dengan nilai yang belakang-belakang ni, nilai WS tu adalah actually considerably small. So, most of the time, we will deem it as negligible. Maksudnya, penambahan nilai ni takkan mempengaruhi sangat pengiraan kita. So, most of the time, we deem it as negligible. Maksudnya, WS tu jadi kosong. Okay? Depends lah, kalau kamu macam soalan test atau soalan exam, kamu kena tengok lah. Kalau dia kata soalan stated deem as negligible, then baru kamu letak WS kosong. Kalau tak, kalau dibagi nilai, kamu kena ganti dengan nilai. Okay? Okay, so ingat. Kalau Q, none ada batik, kira Q. Ada batik, tak payah kira Q. Itu beza dia. WS, kalau diberi nilai, guna. Kalau tak beri nilai, we deem it as negligible. Okay. Next one is FA0. So FA0 yang biasa lah kan, initial molar flow rate A. So nothing new, kamu dah pernah belajar FA0. Okay. Next one, ada benda baru yang kita kena kira again. Okay, this one kalau kamu tengok, dia ada tanda matematik. This is a mathematic symbol of a summation. Summation also means total. Okay, so total of what? Total of theta I CPI. So I yang kecil ni refers to species yang ada dalam kamu punya reactor. Okay, so means kita kena kira theta I CPI, I itu refers to the species in the reactor. However, kita kena tahu apa species yang kita kena kira theta I CPI ni, summation dia. Okay, so first of all, whenever you see summation ni total kan, jumlah kan, so means it will always be tambah, plus. Okay, so whenever you see summation, sebab nanti kamu, bila kita buat yang belakang-belakang, bahagian belakang variable ni ada tambah tolak. So mungkin kamu akan get confused. Just remember mathematic sign, summation means total, means we are adding things, plus. Okay, apa yang kita plus? Okay. Kalau kamu perasan, kamu pernah belajar theta ni kan, kamu pernah belajar macam nak kira theta B. Kadang-kadang kalau ada inert, kamu pun akan kira theta inert. Okay, tapi mungkin kamu lupa apa tu. Theta, katakan kita nak kira theta B. Theta B tu konsep dia adalah initial amount of B over initial amount of A. Itu kalau theta B, reactant B. Kalau kita ada inert, okay, kita nak kira theta I, dia akan jadi initial amount of inert over initial amount of A. Okay, of course kita tak ada theta A, sebab theta A akan jadi 1, sebab theta A akan menjadi initial amount of A over initial amount of A. So 1 lah. But if you realize, when I talk about theta B, theta I, even theta A, I will always say is initial amount. Maksudnya, we can only calculate summation theta I CPI for reactant. And if you have inert dalam kamu punya tindak balas, means any species yang wujud initially, okay, before the reaction occurs, kalau dia ada pada waktu asal, kamu kena kira summation theta I CPI ni. Okay, so kalau kamu lupa CP ni apa, okay, sebab ni energy balance kan, so CP ni kamu pernah belajar, CP is heat capacity at constant pressure, means kamu kira theta Theta, katakan theta spesies, theta B, so theta B darab dengan CPB. Okay, sebab kami ingat, heat capacity at constant pressure ni, setiap spesies, every compound ada heat capacity dia sendiri. Okay, so macam mana penyiraan dia? Okay, saya bagi contoh, katakan you have two reactant. Okay, katakan kamu ada reactant A dan B, dan katakan if you have inert. Okay, so theta I CPI, summation of theta I CPI will be equals to CPA, heat capacity of A at constant pressure, plus theta B CPB. So theta B macam yang biasa kamu kira dalam chapter 3, chapter 4, kita dah selalu kira theta B tu. Tapi jangan lupa darab dengan heat capacity of B at constant pressure, and if you have inert. Kalau tak ada inert, kamu tak payah tambah part belakang. Tapi kalau ada inert, plus theta I CPI. So theta I refers again, kalau theta B, initial amount of B over initial amount of A. So initial amount ni boleh jadi molar flow rate, concentration, mole fraction. Theta I pun sama, dia boleh jadi initial molar flow rate of I, initial concentration of I, initial mole fraction of I. All divided by A juga, initial molar flow rate of A, initial concentration of A, or initial mole fraction of A. Okay. Now, tetapi equation ni kalau kamu perasan, you cannot actually memorize macam tu je, sebab equation ni boleh berubah. What do I mean? Okay. Kes yang pertama yang tadi saya cakap, bila A dan B adalah reactant, maka there will be theta B CPB. However, katakan if your reaction only has one reactant A sahaja, hence summation theta I CPI will be CPA plus theta I CPI if you have inert. So kalau kamu perasan dalam kes kedua dah tak ada untuk theta B CPB, because in the second case we consider that now we no longer have B as a reactant, but in this second case B now is a product. So that's the part yang kadang student akan you have to really understand bagaimana equation ni berubah. Whenever yang tricky-nya part B lah, sebab certain reaction kita ada 2 reactant, certain reaction kita ada 1 reactant. So kamu kena faham bila masa kita kena consider B, bila masa kita tak payah consider B. Ataupun the simplest way untuk kamu ingat, kalau dia tak wujud asal, kalau in the beginning they don't have the initial value, mestilah kamu tak boleh kira theta B tu. Kalau asalnya compound tu tak ada, you cannot calculate theta B. So if you cannot calculate theta B, of course you cannot calculate theta B CPB. Okay, right. So this is on the theta I CPI, summation of theta I CPI. So next one is temperature. Okay, so you can see here, kita ada banyak temperature yang berlainan dalam equation kita. Okay, so previously kita belajar masa kira Q, kita ada TA. So TA tu refers to your heat transfer fluid punya feed temperature. Tu untuk kira Q. Dan in this equation pun ada lagi 3 jenis T yang berlainan. So the first one, the T, yang T biasa saja, this is reaction temperature. Okay, yang T0 adalah initial temperature. Sebab tu, since it is non-isothermal, sebab tu sekarang ada T, ada T0. Kalau isothermal, T dah sama dengan T0. Okay, so that's the difference. Then last one kat belakang ada satu lagi, TR. So TR is refers to reference temperature. Okay, so reference temperature ni adalah, nanti kita akan belajar terms yang kat belakang, delta CP dengan heat of reaction ni. Okay, so both this value, kalau kamu ingat, kamu belajar daripada property table, nilai yang berkaitan dengan energy balance ni macam heat capacity, heat of reaction, dia mesti we will have to, kita tahu nilai tu pada satu reference condition, sebab this value will change with temperature. So bila kita nak guna value tu dalam penyiraan kita, kita kena tahu this value is at what reference temperature. Okay, so that refers to your TR. Okay, so next one. Okay, kita pergi bahagian belakang. Okay, right. So next is Fe0 again. So Fe0 is the initial molar flow rate of A, tak ada berbeza pun. Okay, X is the conversion. Okay, so the next one, delta HRXTR. Okay, so this actually refers to heat of reaction. Sekejap. Okay, so the red one now refers to the heat of reaction at reference temperature. So kamu kena faham, in a reaction, we will have what we call as heat of reaction. Okay, tetapi again, heat of reaction ni dia bukan blanket satu nilai haba untuk semua suhu. Dia tak. This heat of reaction ni memang spesifik kepada suhu apa yang kamu sedang ambil nilai tu. Okay, so that's why we put it heat of reaction at reference temperature. Okay, and sebenarnya, okay, this value, alright, macam mana kita nak tahu nilai heat of reaction? Okay, there are two ways. Normally, kalau your reaction is very common reaction ataupun tindak balas yang memang selalu orang people use, okay, you may obtain the heat of reaction daripada literature. Okay, so you may easily obtain it from literature, tapi don't forget, kamu kena tahu this heat of reaction ni is at what reference temperature. Okay, kamu tak boleh sembarangan ambil tanpa melihat reference temperature itu. Okay, so that's one. Okay, that's one way. Okay, dapat pada literature. Ataupun macam katakan dalam soalan test atau exam, sometimes I will give you directly the value. So kalau dia beri directly, terus gunalah. Kamu dah tak payah fikir. Okay. However, in a real life, more at times, katakan your reaction is new reaction, okay, ataupun you have difficulty in finding the heat of reaction. Okay, there are actually one way for you to find it ataupun to calculate it. Okay, tetapi cara yang kedua ni mungkin kamu akan be a bit confused, but basically kita boleh dapat atau kita boleh kira heat of reaction menggunakan heat of formation. Okay, ataupun kita call enthalpy of formation lah, samalah kerana saya guna heat, kerana saya guna enthalpy, tapi it's the same. We can calculate the heat of reaction using the heat of formation. Okay, apa maksud dia? Okay, kalau kamu pernah belajar CPP and you have used the Felder and Rossi book, okay, bahagian belakang tu ada property table. Kalau kamu perasan, kalau kamu tengok table B1 kan, every compound sebenarnya ada heat of formation dia sendiri tau. Maksudnya, katakan ammonia NH3, dia ada heat formation dia. Katakan hydrochloric acid, sodium hydroxide. Okay. If you check the property table, dia akan beritahu berapa heat of formation untuk ammonia, berapa heat formation for sodium hydroxide. And kalau kamu perasan, even untuk fasa yang berlainan pun heat of formation dia boleh berbeza. Means heat of formation to form ammonia at gas phase and heat formation of ammonia at liquid phase, nilai dia pun boleh berbeza mengikut fasa, dan of course it will be different according to the compound. Okay, so by using this heat of formation of your reactant and your product, you can use this to calculate heat of reaction. Okay, but how do we do this? Okay, kita nak buat ni, right? Okay, first thing, okay, kamu kena, mungkin you will get a little bit confused, but kamu ingat sahaja this mathematics sign delta, segitiga ni kita biasa panggil delta. Okay, so delta normally kita akan cakap it is actually changes. Okay, delta ni masuk, easiest way to see that changes. So kalau changes, mesti ada yang positif, mesti ada yang negatif. Changes is always something is positive, there are something that will be negative. In contrary, kalau tadi yang summation, kalau summation mesti tambah. Kalau delta, mesti ada yang tolak, ada yang tambah. Okay, what do they mean by that? Okay, so I can calculate the heat of reaction by adding the heat of formation of product and minus the heat of formation of your reactant. Means, katakan kamu punya example, kamu ada dua reactant A and B. produk kamu C and D. Okay, so let's say you imagine you check from property table, you will know the heat formation for A, heat formation for B, heat formation for C, heat formation for D. Okay, kamu andaikanlah A tu ammonia. Okay, kamu check okay, berapa ammonia punya heat formation. Katakan B tu let's say hydrochloric acid. So kamu check hydrochloric acid, B ni berapa heat formation dia. Katakan produk dia, okay lah produk dia saya tak sure. Okay, katakan produk dia C kamu check, produk D kamu check. Okay. Heat formation daripada reaktor dengan produk ni kita boleh guna untuk kira heat of reaction. Okay, but you must remember dia mesti positive for product, negative for reactant, and dia ada ratio stoichiometric coefficient, meaning D per A multiply with heat formation of D plus C per A heat formation of C minus B minus because in this case B dan A adalah reactant. So minus B per A heat formation of B minus technically A per A tapi sebab A per A 1 so minus heat formation of A. Okay, so that's how we calculate heat of reaction menggunakan heat of formation of reactant and product. However, equation ni macam yang tadi pun tak fix sebab case B lah. Sebab as I say, B ni dia jadi problem bila kalau first example B is a reactant. But let's say kalau case sekarang we have only one reactant, reactant A. So B dah jadi product. So kalau B is a product, so you see equation tu dah berubah because it will be C per A heat formation of C plus B per A heat formation of B. So now B becomes a positive, a plus, because B in this reaction is now a product. A previous one, B was a reactant, so it becomes negative. Then again minus heat formation of A. So that's how you obtain the heat of reaction using heat of formation. Sebab tu saya kata chapter 6 satu equation, tetapi masalah dia each variable tu ada lagi sub equation dia. Tapi kalau if you do properly, actually not that difficult to solve chapter 6 punya question. Just that don't do mistake lah. Kalau kamu terkira salah satu part, basically the whole thing pun akan salah lah. So that's the only challenge dia. Okay. So contohnya, let's say katakan kita practice, kita nak kira heat of reaction untuk this for this reaction. Okay, let's say we have nitrogen gas plus hydrogen gas, we get ammonia. Okay, kita nak kira how much heat of reaction for this reaction. Okay, so katakan you check from the property table. You determine that heat formation of hydrogen gas 0, heat formation of nitrogen gas are 0, and the heat formation of ammonia negative 11,020 at 25 Celsius. Okay, so just additional information, kalau kamu perasan why hydrogen gas dengan nitrogen gas heat formation dia 0 at 25 Celsius, because nitrogen gas dengan hydrogen gas ni exist naturally at 25 Celsius sebagai hydrogen gas and nitrogen gas, meaning kalau dia wujud secara semula jadi, there's no heat needed either supplied or released untuk membentuk bahan tu pada 25 Celsius. Sebab tu nitrogen gas, hydrogen gas, nitrogen gas, O2 also kalau dia wujud kalau dia wujud naturally pada keadaan itu, so your heat formation akan jadi kosong. Okay. Unlike ammonia, so ammonia heat of formation dia negative 11,020 calorie per mole. Maksudnya for you to form an ammonia gas at 25 Celsius, untuk setiap 1 mole dia akan membebaskan 11,020 kalori untuk setiap mole. Okay. Tanda negatif ni means haba dibebaskan, kalau positif haba is absorbed. Okay. So maksudnya case ni kalau kita nak membentuk ammonia pada suhu 25 Celsius, ammonia gas NH3, for every 1 mole you will actually release 11,020 calorie. Okay. So let's say kamu nak calculate dia punya heat of reaction. Okay. So you will calculate as in this case, 2 reactant, 1 product. So C per A, heat formation of ammonia, your C, minus B per A, heat formation of hydrogen gas, minus again heat formation of nitrogen gas. Don't forget ratio of stoichiometric coefficient. Okay, jangan lupa. Part ni kadang student lupa. Dia kena masuk juga stoichiometric coefficient, and you will get negative 22,040 calorie per mole. So maksudnya apa? Maksudnya for this reaction to occur, for nitrogen gas to react with hydrogen gas to get ammonia, this reaction will release 22,040 calorie per mole. So konsep dia kalau negatif membebaskan haba, positive absorbing heat. So this reaction actually releases heat when ammonia is formed during the reaction. Okay, so next one. The last part of the equation, delta Cp. So konsep sama bila kamu tengok segitiga tu, delta means changes. The easiest word, kamu kena ingat diri sendiri, kalau ada delta mesti ada tambah, mesti ada tolak. Okay, apa yang tambah, apa yang tolak? Kalau tadi tambah tolak heat of formation, tapi untuk Cp tambah tolak Cp. So konsep yang sama, each compound pun dia akan ada heat capacity dia. So heat capacity ni kalau kamu pernah ingat dalam term of CPP, kita ada Cp dengan Cv. Kalau Cv, heat capacity at constant volume. Kalau Cp, heat capacity at constant pressure. So in this calculation, we are using heat capacity at constant pressure. So same concept, kamu imagine kamu pergi tengok property table. Kalau A berapa CP dia, B berapa CP dia, C berapa CP dia, D berapa CP dia, baru kita boleh kira delta CP. So again, positive for product, negative for reactant, and don't forget multiply with the stoichiometric coefficient. So become D per A, heat capacity of D, plus C per A, heat capacity of C, minus B per A, heat capacity of B, minus heat capacity of A. Itu adalah when we have reactant A, reactant B. However, you know, certain reaction, we might have one reactant only, katakan reactant A. So sekarang apa yang berubah? Untuk case C masih samalah, positif C per A, heat capacity of C. But untuk case B dah jadi plus. In this example as B is now a product. So plus B per A, heat capacity of B minus heat capacity of A. Okay, so now same, this example tells you how to calculate juga delta Cp. So kalau kamu tengok macam sama je, just make sure you know your stoichiometric coefficient and you know when is positive, when is negative. Okay. So let's say now, okay, kita try satu soalan, satu contoh. But before I try to the example, to recap back. Okay, so again, kamu dah belajar satu equation yang panjang-panjang ni. Okay, apa kegunaan equation ni? The use of this equation to relate temperature and conversion. Okay, maksudnya if let's say you know your reaction temperature, you use this equation to find conversion, or vice versa. Let's say you know your targeted conversion, you use this equation to find temperature. And as you have just learned, you have to actually solve one by one dulu, baru ganti masuk dalam equation ni. Okay, baru kita boleh solve. And then jangan lupa part belakang tu dia akan sama dengan kosong, barulah kita boleh solve untuk dapat the unknown that we want to find. Okay, so let's say we do one question. Alright, katakan soalan ni kata, given the following reaction, non-adiabatic CSTR. So, kamu kena ingat kalau non-adiabatic kena kira Q. Kalau adiabatic tak payah kira Q. Itu je beza dia. Non-adiabatic calculate Q, adiabatic Q tu 0. Okay, dia kata endothermic liquid phase elementary reaction given here. The reaction proceed successionally to completion. Maksudnya tindak balas ni berlaku sampai lengkap. So what does it mean? Means the reaction will occur until it has completed, or we can say means all your reactant is converted to product. Means A dan B tu habis bertindak balas. Or we can also say this means X tu 100% lah, conversion tu 100%, X tu 1 lah maksud dia. Okay, then dia kata in a single steam jacketed CSTR, and dia kata calculate reactor temperature. Okay, maksudnya dalam soalan ni, dia beritahu kita, dia tahu yang tindak balas ni reacts until complete, means X is 100%, X is 1. They want us to find what is the temperature of the reactor if we want to obtain 100% conversion. Okay, so dia beri kita lah nilai A, nilai TA, nilai U. So kalau kamu tengok nilai yang ada berkaitan dengan jacket, kamu tahu untuk mengira Q. It is used to calculate Q. Then they give us the work done by stirrer, your work shaft, punya nilai. Dia beri kita straight heat of reaction. So kalau dia dah beri straight kita heat of reaction, kamu dah tak payah kira lah, kamu boleh terus guna. Okay, then they give us next in the table, they give us feet. And then in bracket, pound mole per hour. So sama je lah, kamu dah belajar American Engineering Unit. Dia akan guna pound mole, dia akan guna pound, dia akan guna Fahrenheit. Dia akan guna BTU. Okay, this is American Engineering Unit. So, tapi konsep masih sama. Kalau kamu tengok pound mole per hour, dia masih mole per time. So, mole per time, molar flow rate lah. And dia kata feet. So, initial molar flow rate. Maksudnya, initial molar flow rate of A, FA0 10. FB0 pun 10 sebab dua reactant A and B, so FA0 10, FB0 10. They give us feed temperature, means both reactant enters the reactor at 80 Fahrenheit. So kamu kena ingat, sekarang dah non-isothermal, so suhu asal 80 Fahrenheit, in the reactor is no longer 80 Fahrenheit sebab non-isothermal. And then they give us the CP value of A, CP value of B, CP value of C. Okay, so again, come back to the main equation. Maksudnya, nak tahu X, cari T. Okay, so kita kena solve one by one. Okay, so first kita solve Q. So Q, kita kena cari dulu dia punya equation kan. So Q is equals to heat transfer coefficient multiply with jacket area in bracket heat transfer fluid inlet temperature minus reactor temperature. Okay, so U 150 from the question, A is 10, okay, in bracket, heat transfer fluid punya temperature, feed temperature of heat transfer fluid kita adalah 365.9, okay, minus T. T kita tak tahu, we don't know the value of T. T tu yang kita nak cari kan, so T tu kita biarkan. Okay, so kita solve dah part untuk Q. So yang sub equation first kita dah settle. Okay, next WS dah bagi is given directly 63,664. So tak payah kira, terus ganti nilai. Next FA0. So FA0 daripada table 10, settle. Next X is 1 lah. Sorry, belum X lagi. Theta I CPI, summation of theta I CPI. Okay, so summation theta I CPI. In this case, initially hanya ada A dan B, tak ada inert. Okay, they didn't mention anything about inert. So it's only reactant A and reactant B. So summation theta I CPI ni equals to CPA. Technically theta A CPA, tapi theta A itu 1. That's why we don't write down theta A. Understandable is 1. So CPA plus theta B CPB. Okay, so means kita kena multiply theta B dengan CPB. So how to find theta B? So kan saya kata theta B kamu boleh cari depends on the information given. Either is given molar flow rate or given concentration or mole fraction. Tapi dia mesti initial value. So in this case, they give us initial molar flow rate of A and B. FA0 was 10, FB0 was 10. So this can be used to calculate theta B. So theta B 10 divided by 10 is 1. So you will replace CPA 51, theta B 1, CPB 44. So you will get summation theta I CPI as 95. So done. Okay, next one kita tengok kat belakang. T kita nak cari, kita biarkan. T0 feed temperature. Okay, feed temperature daripada soalan 80. Okay, so suhu asal sebelum tindak balas berlaku. So 80. FA0 again, FA0 10. X1 sebab dia kata proceed to completion means semua reactant is converted into product. Your conversion is 100% is 1. Okay, next. Heat of reaction. So heat of reaction is actually dah diberi dan soalan ni. So yang laki yang given tadi 20,000 tak payah kira. Okay, so 20,000 done. So belakang delta CP. Okay, so delta CP as I told you, kamu just ingat kalau ada delta tu mesti ada tambah, mesti ada tolak. So plus for product, negative for reactant. So C per A multiply with heat capacity of C minus B per A, heat capacity of B minus heat capacity of A. So C per A 2, multiply with 47.5, tengok daripada table, minus B per A 1, multiply with 44, multiply with minus with CPA 51, you get 0. So happen dalam penyiraan ni delta CP kita kosong. Okay, so kalau kamu perasan soalan ni dia tak beri kita reference temperature. So happen dia tak beri kita reference temperature, tetapi tak mengapa pun dalam soalan ni, because so happen delta CP kosong. So kalau kosong, whatever yang darat dalam bracket ni dah confirm kosong jugalah. That's why dia tak beri kita nilai reference temperature, is because delta CP dalam soalan ni adalah kosong. Okay. Tapi you still have to solve lah kan. Okay, so once you calculated everything, you substitute inside. So kamu tengok tadi yang Q yang kita kira 1005, 365.9 minus T, kita ganti Q dengan nilai yang tadi, minus WS ganti juga, ganti minus FA0 10, ganti theta I CPI summation theta I CPI 95, in bracket T masih ada minus feed temperature 80, here minus FA0 again 10, X1 heat of reaction 20,000 yang diberi plus delta CP kosong. Okay, so kamu tengok dalam equation ni yang penting hanya satu unknown saja, hanya temperature je. Yang lain semua kita dah solve. Barulah kita boleh dapat nilai temperature, because one equation, one unknown, then only you can solve. So you get the temperature of your reactor as 147.4 Fahrenheit. So this is example how we use the energy balance equation to actually find, okay, either again X, either diberi X cari T atau diberi T cari X. Okay. So done this example. Okay, so to recap back, okay, kamu kena faham juga balik, okay, kenapa kita ada equation yang baru ni. Okay, so again, sebab alright, tadi saya katakan kamu kalau kita nak cari volume reactor, kita ada terlalu banyak unknown yang kita tak tahu sebab we don't know T and X. Okay, so now that we have the energy balance equation, okay, so what you do is, okay, if let's say soalan tu kita tahu conversion, or let's say in the real application, you know your targeted conversion, okay, and you know this is non-isothermal. So you use the energy balance equation yang saya ajar tadi untuk cari conversion dulu. Okay. Dah dapat conversion, step kedua, since kamu, cari conversion pula. Kalau tahu conversion, kamu guna energy balance equation ni untuk cari temperature. Okay, so kalau saya nak target conversion ni, I use this equation, I will know my reaction temperature. Tahu reaction temperature, baru kamu boleh kira K. So, ni yang kamu kena ingat. Why it's so important to have the energy balance equation is because once I know reaction temperature, then only I can calculate my K. So kalau dah calculate K, barulah kita boleh cari volume reactor. So that's why we need the energy balance equation, is that we can find the correlation between T and X, and then we get K, and then we can solve to find the volume. Okay. Another way, vice versa, katakan kamu tahu temperature. So kamu tahu temperature, tak tahu conversion. So let's say you know the reaction temperature, but you don't know the conversion. You can also calculate using the energy balance equation, of which you will obtain X. So kalau dapat X, dah tahu T, again boleh kira K, boleh kira volume reactor. Okay, so done on the how do we use the energy balance equation and to relate to the design of reactor. Okay, so the last part for today is, tadi kita belajar non-adiabatic. Kalau non-adiabatic means Q ada nilai, means there are heat supplied to the reactor, hence Q tu kita kena kira. Okay. Another case is what we call as adiabatic system. So means adiabatic system, no heat loss or no heat supplied to the reactor. Okay, in this case Q is 0. Okay, but how it influence our design equation, our energy balance equation, maksudnya kan tadi equation asal ada Q, tapi sekarang Q tu jadi kosong lah. Okay, that's the only difference. Non-adiabatic kira Q, adiabatic dah tak payah kira Q. Part lain dalam equation tu masih sama untuk kamu mengira, and the aim, the target is still the same. You know temperature, you find conversion, or you know conversion, you find temperature. Okay, so to finish up, okay, one last question for today before we finish. Okay, let's say soalan ni kata non-isothermal liquid phase reaction. Okay, we are using steam jacketed CSTR. Dia kata adiabatic system. So bila kamu baca adiabatic je, kamu terus tahu Q2 kosong. Okay. Dan dia beri kita information lagi. Dia kata assume work done by stirrer negligible. Maksudnya WS work shaft is 0 sebab work done is negligible. So WS kosong dan sebab adiabatic Q pun kosong. Okay, dia kata determine the reaction temperature and subsequently reactor volume if the reaction obeys elementary rate law. So kita kira temperature, dia suruh kita kira volume CSTR kita. Okay, so let's see information dia beri. Okay, so dia beri kita initial flow rate of A 2.8527 mole per minute. So FA0, okay, FA0 2.8527. Kalau kamu perasan, tindak balas ni ada satu reaktan sahaja. Okay, so easier sikit lah bila ada satu reaktan sahaja. Dia beri kita volumetric flow rate, okay, V0, okay, dia beri kita conversion. Okay, so kan saya kata energy balance equation ni either beri temperature cari conversion atau beri conversion cari temperature. So dalam soalan ni, they gave us the conversion, we want to find the temperature. They give us the K, but the K is at 350 Kelvin. Okay. They give us activation energy. They give us feed temperature. Means temperature asal before the reaction occurs is 303 Kelvin. Okay. Then in the table, dia beri kita enthalpy of formation, heat of formation. So means kalau dia beri heat of formation tu, kita nak guna untuk kira heat of reaction lah. So enthalpy A, heat of formation of A, heat formation of B, heat formation of C. And don't forget, dia beritahu heat of formation ni pada reference temperature 298 Kelvin. Okay, so this is the reference temperature kita akan guna dalam equation kita. And then data CP juga dia beri, CP for A, CP for B, CP for C. So CP untuk kira data CP lah dan juga untuk kira yang theta ICPI, and then enthalpy formation untuk kira heat of reaction. Okay. So again one by one kita kira. Okay, so first Q 0, WS pun 0. Okay, FA0 dia beri 2.8527. Okay, theta ICPI. Okay, so theta ICPI dalam case ni satu reactant, tak ada inert. Okay, so kadang kamu kena berhati-hati. Kadang-kadang satu reactant mungkin ada inert. Kalau ada inert kena kira sekali. Ataupun kalau kamu tengok dalam soalan tu, spesies tu tak terlibat dalam tindak balas, tapi dia ada wujud pada waktu asal, you have to include in the calculation for the theta ICPI. But in this example, it was only one reactant. There are no other compound. So theta ICPI jadi terus CPA sebab sepatutnya theta ACPA, but theta A is 1. So it become theta ACPA, terus ambil nilai CPA which is 0.1. So done. Okay, so in bracket T kita nak cari, we leave it. T0 303, okay, the feed temperature. Yang belakang FA0 is 2.8527 again. Conversion 0.7011 given in the question. Heat of reaction ni kita kena kira. So heat reaction ni satu reactant dua produk. So positive for product B, product C, and negative for reactant A. And heat reaction ni kalau soalan tadi dia beri kita directly, this question you have to calculate by yourself. So kita kira lah. So C per A, heat formation of C, plus B per A, heat formation of B, minus heat formation of A. So you calculate, you get negative 55. So again, heat of reaction ni boleh jadi negatif, boleh jadi positif, which is very normal because negative signify exothermic, positive signify endothermic. So either way is also possible untuk nilai untuk dapat negatif atau positif lah. Next, data CP. So data CP pun sama je, positive for product, negative for reactant, but you will calculate using the CP lah. Okay, so you calculate, you get 0.25. So dah solve semua. Okay, kat belakang ni T kita nak cari. TR reference temperature. Tengok soalan. Reference temperature kata 298. Okay, so 298. So again, you put in everything into the final equation. You make sure there's only one unknown, which is T. Walaupun T tu muncul 2 kali atau 3 kali dalam equation, tak apa. Tapi dia masih T yang sama. Dia jadi masalah bila ada T, ada X dan tak boleh. Kalau satu equation, satu je unknown. If you solve this, you will get the temperature 439.9. Okay, so temperature dah solve, tapi belum siap lagi sebab dia suruh kita cari volume reactor. Okay, so volume reactor, kamu tahu CSTR dia sama dengan FA0 per minus R, FA0X per minus RA. Dia kata obeys elementary rate law. So rate law dia minus RA KCA square. Dan CA akan sama dengan CA0 1 minus X. So first thing first, kamu dah tahu, kita dah tahu reaction temperature kita dah boleh kira K. Okay, sebelum ni itu masalahnya, tak tahu temperature, tak boleh kira K. So kita dah tahu reaction temperature, kita dah boleh kira K. Tapi dalam soalan ni a bit tricky. Dia sebenarnya dah pernah beri kita nilai K, tapi K tu pada 350 Kelvin. So kamu kena betul-betul ingat, okay, K yang diberi was at 350, but my reaction temperature that we calculated was 439.9. So means kamu kena kira K yang baru tu. Okay, so you will use the equation yang Arrhenius lang K2 equals to K1 exponential EA per R in bracket 1 per T1 minus 1 per T2. Okay, so you will calculate the new K, you akan dapat 0.6393. Okay, so means diberi kita K pada suhu yang lain, kita kena cari K baru pada suhu yang kita dah kira. And then once you done that, you can already solve lah everything kamu dah boleh solve, kamu ganti je ke dalam equation. So actually yang penting dalam soalan ni, kenapa kita tak boleh kira volume was because we don't know reaction temperature. Don't know reaction temperature, I cannot calculate K. I don't know K, I cannot kira the volume. So once I know temperature, I can calculate K. I can already solve to find the volume of the CSTR. Okay. So done for chapter 6. So actually chapter 6 pun tak susah dan memang ni lah chapter last yang ada pengiraan. So another one tutorial for chapter 6 and then we are done for calculation. Chapter 7, 8 is very easy. It's just understanding chapter membaca lah. Okay. So I'm done for tonight. So hopefully I can see you this weekend for one class for us to settle tutorial chapter 6. Okay. Ada soalan tak Aizat dengan Hidayah? Ada. Alright. Aizat, adakah Aizat? Oh, Aizat tak boleh tu. Alright. Okay. So I see you hopefully this weekend lah. Have a good night. Have a good rest Aizat. Hidayah, take care. Nanti besok saya beri kamu assumption punya nilai untuk kamu punya mini project. So kalau sempat hantar Jumaat lah. Kalau tak sempat minggu by weekend pun okay.
Okay, I try sebaik mungkin lah.
Okay, no problem. Good night. Bye-bye.
Bye.